last time. 4-bus power system. We have one infinite bus. We have two PQ buses, which we also will call load buses. And then we have one PV bus, which has both a generator and a load. Okay. Again, if you remember, the hierarchy goes, if something's a slack bus, doesn't matter what else is there, it's a slack bus. If something has a generator, it's going to be a PV bus, doesn't matter what else is there. And then the lowest tier in the hierarchy is if something only has loads, then it ends up being a PQ bus. And so for this here, we ask ourselves, how many state variables are there? There's going to be how many for this bus that we have to solve for? None, right? For both of these, they're going to have how many each? Two, right? Because we have to solve for the magnitude and the angle. And then for this, just one, which is going to be the angle. So 5. Now, the thing about Gauss-Seidel is even though we only have 5 variables to solve for, we group, we do all the calculations in a polar form, right? So, and this is different when we get to Newton-Raphson, you'll see everything's split up, so we can take more advantage of the fact that this is 5 and not 6. But for Gauss-Seidel, we're sort of forced into solving for 6, the 6th one being the voltage magnitude at this bus each time, and then essentially throwing that value away and replacing it with the set value each time. So we will have 5 state variables, but for Gauss-Seidel, really the number of equations will be based on the number of buses that we have, which is 3 that we have to solve for. Regardless of whether it's Gauss-Seidel or Newton-Raphson, we still get away with not having to deal with the infinite bus, which is nice. Now, what we had done so far was dealt with the lines. So we are going to be assuming a what's called a pi transmission line model for everything here. And in the pi transmission line model, we have a series element, and then we have 2 shunt elements. And so what happens is that when we're formulating our Y-bus matrix for bus number 1, okay, for example, the diagonal element will include every single impedance or admittance that touches or is adjacent to bus number 1, right? That's how we define the diagonal elements. The diagonal elements are everything that's connected to it. The off-diagonal elements are minus whatever the spanning impedance is. So for bus number 1, if there's only 2 lines connected to it, line 1, 2 and line 1, 3, we'll have 4 impedances that are connected. This, the shunt element at 1, or on the first half of the line, this series element, this shunt element, and this series element. Okay. The other ones on the other side, they are not adjacent directly to 1. They're going to end up being adjacent to 3 and to 2, respectively. So therefore, when we calculate, this is just defining the first row of the Y-bus matrix, we end up with 4 elements. Series element, shunt element, shunt element. And then the off diagonals, negative y12, negative y13, and actually I forgot, but there should be a negative y14, which would be 0 because there's no connection between the first and the fourth is this dead? I'll charge it for a second while I talk. Okay. And then, so when we go through and we define the entire Y-bus matrix, what we will end up with is a 4 by 4 matrix, which makes sense because there's 4 buses. And all the diagonal elements will be significantly longer, and the off diagonals shorter, and the zeros will be placed according to where there's no connection. So if we look here, there's no connection between 2 and 3. So element 2, 3, you would expect to be 0. So let's see that. So 1, 2, 1, 2, 3. So there's your 0 right there. That one. That's a 0. Okay, so then what we did was we completed the Y-bus matrix symbolically. So now you can see here all of the impedances. Actually, we're working with admittances in this case. Are placed into the matrix. One note is that we started defining this new value called Y shunt 1 or Y shunt 2, Y shunt 3. And that's essentially just all of the shunt elements that are on the side of the lines that are facing the bus. It's just another way that they can define the Y-bus, the admittance elements for us. In one way, it's a little bit simpler because you don't have to add them together. That way they can just give you the series elements, and then they'll give you 4 shunt elements, and you don't have to split it up yourself. Regardless, it's important to know what each one means and how each one can be used differently. For later on problems that fall into this range, a lot of times they'll just go ahead and give you the Y-bus matrix, but I mean, forming it is important. And so we had stopped at this point where finally we got the Y-bus matrix that we were looking for. It's symmetrical, and so the x's would just be the same value as whatever it would be when the indices are flipped. All right. Let's see if my pen here is charged. Okay, good. All right, so let's pick up from here. Plug it back in. Okay. So, what's the next thing that we have to do for this problem? Next thing that we have to do is start setting up the equations. So, how many equations? 3 again, like we said before. And so let's go ahead and do that. I'm going to start off with the PQ buses and leave the PV bus for last. And the reason for that is because we know we have this little bit of an extra mini step with the PV bus where we have to handle the fact that we don't have a Q injection value defined, and so we'll have to figure that out. So let's do the next step, which is all right, so what is the general form of the Gauss-Seidel? Let's write that down And we'll use that as the model for doing all this here. So the general form for Gauss-Seidel looks like this. It's V I of k equals 1 over y bus I times pi injection minus j qi injection divided by v I to the k minus 1 conjugate. We're going to subtract from that the sum of m to whatever the bus is before the one that we're looking at, YIM bus, times VM bus. So these are the values that have already been updated. Then the ones that have not been updated. So that'll be the sum from I plus 1, so going past us, our current bus. Now the one thing about the way this is labeled and the use of the m's, it assumes that you're doing everything in the numerical order, right? It assumes that if you have buses 1, 2, 3, 4, 5, 6, you're updating 1 first, then 2, then 3, then 4. Otherwise, right, the updated values wouldn't be the ones less than I minus 1, and the unupdated ones wouldn't be greater than I plus 1, right? If you just update them in a random order, like 2, 6, 5, 4, then it would be hard to define the sum because you would have to just say for all that are updated and then for all that are not updated. All right, and then so bus number 2 is the first one that we're going to update, and so when we start, there's no values that are already updated. So for bus number 2, we're only going to have the first term and the third term. And yeah, that's pretty much it. So we can go ahead and start doing this for real.
I have a quick question.
Yep.
Does this only work if the infinite bus is bus number 1?
No, because actually for the infinite bus is really not considered. The infinite bus is just given like carte blanche. It counts as iteration k plus 1, as all iterations. So you know all the iteration values of the infinite bus.
Okay.
The only difference would be you would start at bus number 1 as opposed to starting at bus number 2. But it shouldn't screw up the definition of the Gauss-Seidel. And updating the buses out of order doesn't mess up the Gauss-Seidel either. It just makes the formulation, I mean, you would have to write M for all unupdated buses and M for all unupdated. It would just be a little bit more difficult to state it mathematically. All right, so let's fill in the values. So which ones are the PQ buses? That's 2 and 3. Okay, so V2 for iteration 1. And I'm not going to state it explicitly, but real quickly I can throw it in here. we're going to use a flat start initial condition. So all of our V0 values, 0th iteration values, will be 1 with an angle of 0. Okay, so all right, so now we need to get the 2-2 element of the Y-bus matrix. So we go up here, and that's this guy. So 8.99 minus J, 44.84. All right. Next, P injection minus JQ injection. So these values are given to us. I don't think I had written them out. There's a table that actually gives them to us. So what I'm going to do is I'm going to write them over here to the side. These are other inputs that we have. I'm going to try to write it pretty small. So we have bus 1. We have bus 2, we have bus 3, we have bus 4. They give it to us as such. They say that we have the generation and we have the load. And then we have the nominal voltage, which for buses 2 and 3 literally means nothing, right? The nominal voltage for buses 2 and 3, it might give us a good starting point, but other than that, I mean, the voltage is not defined. Okay, so, and then there's P in megawatts, there's Q in megavar, there's going to be P in megawatts, and there's going to be Q in megavar, and then the voltage is over here. Okay, so let's write down the values. So for bus number 1, all of these are undefined. We don't really care what they are. It's a slack bus anyway. The nominal voltage is 1.0 with an angle of 0. So that's our slack bus. For bus number 2, there's no generation. There is 170 megawatts of load and 105.35 megavar. Here it's again 1.0 with an angle of 0, but this value in the long term, or well, not long term, it doesn't help us with the problem at all. Bus number 3 has no generation. It has a load of 200 megawatts, and it has a real load of 123.94. Same thing, 1.0 with an angle of 0, which is not really going to come into play. And then lastly, we have the generation, so 318. This value doesn't matter because we're not going to be using Qs. It has a load of 80, and it has a reactive load, but this also is not going to matter. Okay? And lastly, they give us the nominal voltage. Now this is going to be an important value because we're going to be using the magnitude part of it. So if we were to circle in green the values that are important to our analysis, right? This, because the voltage of the slack bus is going to play a major role in this. For the load, in both instances, the P and Q values obviously are going to be important. And then for the generator, it's going to be the voltage magnitude, and then these two. More importantly, it's going to be the difference between these two. The delta P will be, so the net generation will be 318 minus 80, which is 238 megawatts. So, from a net standpoint, that's the real value that we're looking at, is the 238. All right, so this is all right, so now let's get the values that we need. So 170 and 105, right? Those are the two values that we need for this bus number 2. So 170, 105.35. We divide by the S base there because we've already decided we're going to do this problem in per unit. The voltages are all in per unit. And so the way it works is if you're going to use per unit voltages, you need to have everything be in per unit. So we're just going to go ahead and divide by the S base, which is given to us up top, of 100 megavolt amps.
Do we have to change the minutes per unit?
The what?
The minutes for the Y bus?
Yes, actually. No, that's already in per unit.
Oh, okay.
Everything's already. Now let me make a note there. But if it weren't, yes, you would have to. Okay, then we're going to divide by whatever the previous version of voltage 2 is, and that's going to be 1.0 with an angle of 0 degrees. That is our value of V2, 0, the initial condition. And now we expect there to be two other components because bus 2 is connected to two other buses. And so those buses are 1 and 4. So let's say here y, well, I want the actual value. So let's go and find y bus 2, 1. So y bus 2, 1 is here. So negative 3.82 J 19.08. And then we're going to multiply that by, so what's M in this case? M is the second subscript, So that means it's 1. So we'll have V 1 initial condition, and so I'm trying to put in values. Keep forgetting. And so that's going to be 1 with an angle of 0, and that is because it's the infinite bus. Then we subtract out one more value, and that's going to be y24. Oh, is 2 not connected to 4? 2 is connected to 3? No, 2 is connected to 4. Yeah, 2, 4. So negative 5.17 plus J 25.85. And we're going to multiply that by 1.02 with an angle of 0. If you remember, we know that this will always be 1.02. If you look back up here, 1.02. Okay, so that's the first equation. And so I'm just trying to reconcile what I have in my notes with, okay, here we go. 899 for, that's right, 19.8, 7. Okay, so all those values, correct? And so if we do the calculation for it, and you can check it in MATLAB if you want to, you end up with 0.9836 minus J 0.0323, which is equal to and that's in radians, the angle. And so that's the first update. We have to do the same thing for bus 3. This one we can do a little bit more quickly. So bus 3 is, what's our 3 element? 8.19 minus J 40.86. Let's find our P and Q values for bus 3. That's going to be 200 and 123.94. Again, divided by the 100 MVA. We're going to divide it by whatever the initial condition for bus V3 is, which is going to be 1 with an angle of 0 again. Bus 3 is connected to bus 1 and to bus 4. So let's start off with 3, 1. So what's the value of 3, 1? It's negative 5.17 plus J 25.85. And we're going to multiply that by the voltage at bus 1, which is always going to be one with an angle of 0. We're going to subtract out. Now we'll do the element 3, 4. And that's 1, 2, 3, 1, 2, 3 is negative 3.02 plus 15.11. And we're going to multiply that by 1.02 with an angle of 0, again, because we have to take into account the voltage magnitude there. All right, so let me check all those values. 8.19, that's right. Okay, now one thing, sorry, that I was not being very diligent about. The injections are assumed to be positive. So when we have the load injections, they have to be properly denoted as being negative. And we'll see that when we do bus number 4, and we have power injections that are a result of a generator, those will be positive injections going in. Okay, that's 1. Okay, so that's all good, and we end up with 0.9712 minus J 0.0417, and that gives us 0.9720 as a magnitude with an angle of negative 1 radians. Okay, so we've completed one iteration for the 2 buses.
Do we not have to do bus 4?
We are. We're going to do that right now.
Oh.
And, one weird thing about this problem is that actually Gauss-Seidel doesn't play into the updated voltages 2 and 3, right? Because they aren't connected to one another. So we didn't get a chance to use the update for voltage 2 inside of the update expression for 3. But we'll see when we do 4, it'll use both of the updated values. Okay, so now let's do bus number 4. Okay, we know the P4 injection. That up above is 238 megawatts, right? It's the 318 minus the 80. So we can go ahead and write that down, 238 megawatts. Okay, so the little intermediate step here. So now we're going to have to go calculate a value of Q injection for this bus, which is going to be based off of the voltages, and then plug that into the update and use it to update, which is, again, seems like a little bit of a backwards process, and it is a little bit inefficient. This is another advantage we'll see when we move on to the Newton-Raphson method, is we don't have to do any of this. When we're working in the Newton-Raphson method, what will happen is the Q value and the V magnitude value will just completely fall out of the analysis. You'll take that row and that column of the matrices and you'll just delete, and everything will shrink by 1. Okay, so what is Q4? Calc. We have an expression for that. It's going to be the sum, so it's going to be V4, and I'm going to give this an iteration number. Hold on. Well, actually, I don't need to give the iteration number. It's going to be V4, 0 times the sum we only need the imaginary part, so I should state that. It's going to be V4 times the sum of M, or I could say K equals 0 to N for all the different buses, of Y bus 4K times voltage K iteration 1. So that's an expression from the book. And, well, bus 4 isn't updated yet, so I'm going to, you know what I'm going to do for the sake of simplicity? Instead of splitting it up into 2 different sums, I'm just going to say whatever the newest available is, use that. And so where is this in the notes? It's here. Equation 215, okay? So that tells us how to calculate the Q value. Now we're going through this step by step by hand because it's a good learning exercise. But I mean, it's very inefficient in terms of calculating. So when it comes to a quiz or an exam, you know, I don't have any issue. I'll probably be pretty clear about what tools you can and can't use. But using MATLAB for solving these is not going to be problematic. Definitely using a calculator is not going to be problematic. Yeah.
Do you know what room we're going to be in for final exam?
Actually, I talked about that at the beginning, right? I think maybe you just stepped in. Anyway, no worries. So I think this is most 99% going to be a take-home exam, because everyone's going to be using laptops, and it really doesn't make much sense. And it's all open book and anything. But for the final exam, it's going to be like a 3-hour open and close type thing. It's not going to be like a variable window. We don't necessarily have to do it the 3 hours because it's early in the morning on the 10th or the 20th. If we can find a time where everybody else has a 3-hour block or 2.5-hour block, that's fine with me, and we can worry about that later on next week or something like that. But yeah, that'll most likely be what it is, like a 3-hour block. Everybody has to log on, be there at the same time, and all that type of stuff. Okay, so back on to what we were doing. So to calculate the Q, all right, so V4 0 is 1.02 with an angle of 0. We're going to multiply that by, we have 3 different elements. So Y4 1 doesn't exist. So what I'm going to do is I'm just going to say Y4 1 bus times V1. Right, that goes away. We don't have that element. Next, Y42. So Y42 is negative 5.17 plus J 25.85. And now we're going to pull in our updated value of V2, which is 0.9841 with an angle of negative 0.0328 radians. Okay, we're going to add to that 4.3. And so 4.3 is negative 3.02 plus J 1511. And we're going to multiply that by our updated value for V3, which is 0.9720 with an angle of negative 0.0403 radians. And we can't forget our self-admittance. So Y44, and that is 819 minus J 40.86. And we can multiply that by 1.02 with an angle of 0. And so here is our 4,2 element. Here is our 4,3 element. And here is our 4,4 element. And so when we run that all through, let me check the values to see it makes sense. 5.17, yeah, okay, 3.12. Yeah. All right, so when we run that all through, we end up with a value of 1.31 per unit. Okay, now,
Do we just ignore the angle on that?
yeah, see, just the imaginary part.
Oh, okay.
Yeah, you have to just take the imaginary part. Because what this is doing is this is going to calculate the S calc. But we know what P is. Okay. So, now, now we can go ahead and do it the same way we did the other ones. So V, 4, 1. And if you want to really be accurate, we're only updating the angle of V41. And that is going to be equal to the angle I know I'm using different notation, but I don't want to put a long line under the whole equation. It'll look ugly. So the angle component of, and now we just do the regular update. So we will have 1 over y44, so that's 8.19 minus j40.86. Again, right, that's y44 bus. We're going to multiply that by our 238 divided by 100 MVA. The reason why I'm only dividing that one is because remember our Q is already in per unit. Minus 1.3J 1.31, right? So this is P for injection. This is our Q for calculated. We're going to divide that by our previous value of V4, which is 1.02 with an angle of 0. That is V4 initial condition. Then we are going to have, so bus 4 is connected to 2 and to 3. So first thing is 4-2. We have those admittances already available to us. They're written right above. So negative 5.17 plus J 25.85 times now the 0.9841 with an angle of negative 0.0328 radians. So this is Y42 bus. This is V21. We are going to add to that, so I'll put a dot, 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 minus negative 3.02 plus J15.11, and now 0.9720 with an angle of negative 0.0403 radians. And that's it. So this is our Y bus 4-3, and this is our V3 to the 1. And what we end up with is, and I'll go ahead and show what the updated angle would magnitude would be, even though we're not going to use it. So that goes away. It's 1.0228, and we'll keep the angle, which is 0.0122 radians. So So we keep going until the difference between the updated and the previous values for the voltages at all the buses drops below some prescribed threshold. And you can set that however you see fit. For smaller analyses, it probably won't make that much of a difference because it'll get pretty close to zero, and it will do so relatively quickly. When you have analyses where your values may not be perfect, okay, meaning that you're working with a real system and you're estimating some of the injections and you're estimating some of the line values, then you might want to set your threshold a little bit bigger because you might have a little bit more of a problem getting to an exact convergence. So, I mean, that's the general process. That's obviously only one iteration. I think this could be something I ask on, on the exam. I'd probably maybe ask you to only update like one bus, because by hand, because one bus, wouldn't take you that long, and it would still require you to understand like how to essentially use the equation in any circumstance. If I wanted to be tricky, I could say, well, I'm going to make you update the PV bus, because that's the one that's a little bit more tricky. And if I ask you to do something by hand, that doesn't mean that you can't use MATLAB for the calculations. It just means that you have to show me the steps by hand. Okay, so, I mean, that's, I'll give you some homework problems for Gauss-Seidel, but if you can understand this example, this is more or less kind of the worst case scenario as far as this class is concerned. We're not going to be doing, we're not going to have the opportunity to do really, really large systems, and this has all the parts. It has infinite bus, 2 PQ buses, it has a PV bus, so that's pretty much the whole thing. Obviously, I'll post these notes online, take a look at them, but this is like the real resource that you would want to use for this type of problem. And the exact same work is done in the notes. If you scroll up, you'll see it's all up here. Same numbers and everything. Okay, if you're interested, you can actually run the MATLAB code, which I've made available to you. And so this MATLAB code will run this example. So you can see the y bus is defined, etc., etc. So what happens? That's what it looks like. So it only takes about 10 iterations in order to come to converge. You'll note that the voltage angle takes a little bit longer than the voltage magnitude in order to converge. That's an issue that we can actually fix in the Newton-Raphson method. Because in the Newton-Raphson method, what we could do is we can actually set different coefficients for the update of the angles and the magnitudes. And if we see over and over again that the angles are taking longer to converge, we can increase the update, the gain of each update, or the effect of each individual update. And then you can see the solutions. There's 2 solutions for the magnitude, right? And there's 3 solutions for the angle, because we don't have the V magnitude for bus 4. We don't have to calculate.
How do we know when to calculate the Q versus just use what they give us?
PV bus. If it's
On PVs?
only on the PV bus.
Okay.
Because the PV bus is the only time that that value is not given. And it's a little bit tricky because they may give you a table where they list a Q value, but if they tell you it's a PV bus, that Q value is not part of the model. You understand what I'm saying? It's a little bit of a weird. I mean, I don't think I would present it to you in that way, but it could be presented in that way, where they would say, oh, well, this is the nominal Q value for the PV bus. That doesn't matter. It's in the same way that they gave us a nominal voltage for the PQ bus. That's it's a nominal value, but that's not part of the model that we're using for that bus, so it doesn't matter. If you go in the iPad notes where we circled the values with the green, those are the only ones that matter. Everything else, they can give you as many values as they want, but it's irrelevant to the model at that point. Okay, so that makes sense, more or less. Spend some time going through it. And the great thing about it is when you combine the Gauss-Seidel method together with the Deese example that we did, it's a really useful tool for solving nonlinear systems of equations. If you take a step back and just look at the generic formulation, you can use that to solve any nonlinear system of equations. Okay. So Newton-Raphson method. What's the difference? The Newton-Raphson method is a method to solve nonlinear systems based on a Taylor series expansion. It does the same job. Its formulation is a little bit different. It's a matrix-based formulation, and one that, so for example, the Gauss-Seidel that we did for that example, right? The formulation would be drastically different if the lines took different paths, right? If there was a connection between buses 2 and 3, then there would be an additional term in the update expression for those individual voltages. And if buses 2 and 4 were both PV buses, then that would also change the formulation, right? So there's a lot of different things that you have to be accounting for when you're using the Gauss-Seidel method. The Newton-Raphson is a little bit less like that. It's sort of like, it may be a little bit more difficult up front to understand the structure, but it's like just almost like a stamp. Like you just boom, 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 boom. Same thing over and over again, and you just plug in the values. So let's consider this example here. So let's say our goal is to find the values of x1 and x2 which satisfy the constraint g equals 0 below. Okay, and this is equation 229. So to give a real world or a practical example of that, it could be sine of x plus x squared minus 3 equals 0, and then x1 cubed plus x2 to the 4th minus 6 equals 0. There's two generic nonlinear expressions, both of them equal to 0. Okay? So we could solve those using a method similar to the Gauss-Seidel, but maybe there's another way that we could try to do it. So what would happen if we tried to approximate this using a Taylor series expansion? The Taylor series expansion is the same tool that we use for linearization, right? It says that a function, any function, is equal to its the point at its value at an operating point plus the first derivative times the difference between your point and the operating point plus second derivative, third derivative. And if you take that all the way out to the infinite number of derivatives, then you end up exactly with the expression that you started with, right? But for the purposes for linearization, what we do is we cut it off. Okay, we use an imperfect or an approximation of the function. So here's what the Taylor series expansion looks like for G1 and G2. G1 is the top half, G2 is the bottom half. Our operating point we're going to call x1, 0, x2, 0. So that's our linearization point. And since this function is a function of two different variables, we have to do the derivative with respect to both. So for the first one, g1, the approximation is g1 x1 x2 plus the derivative of g1 with respect to x1 times delta x1, the derivative of g1 with respect to x2 times delta x2, and then plus, boom, 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 going on down the line, second derivatives, third derivatives, fourth derivatives, which we're not going to consider. Then we could do the same thing for g2. g2 at the operating point plus dg2 dx1 plus dg2 dx2, going on down the line further and further and further. Right? This is the exact same thing, well, not the exact, but it's the two-variable version of Taylor Swift. Exactly. Right? Of this. The single variable version looks like that. Probably more familiar with that version right there. F of A equals, or f of x, well, no, f of A equals, well, A is the operating point. No, f of x, okay, they'd use x. F of x is equal to f at the operating point plus the first derivative of a, x minus a, boom, 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 going on the line. So now, in the picture that I showed, or in the expression that I showed, it was only the zeroth in the first term. We didn't show any of these other terms. But this is a single variable example. So all we have to worry about is df dx. When we're using two variables, we have to do df dx1 and df dx2. Okay. And that's what's shown here. If it were a three-variable problem, it would be dg1 dx1, dg1 dx2, dg1 dx3, going on down the line. So if we use only the first order approximation, we can take this right here and we can put it into this matrix looking form. So G1 and G2, and the star just means the solution. We can just call it x1, x2, is approximately equal to, the stars takes care of the approximately equal, but it's easier to think about it as is approximately equal to the functions at the linearization point, or the operating point, 0, 0, 0, 0, plus, and now you can see we take all the derivatives, we put them in a matrix, and we multiply them by the differences between x1 and the operating point. This is like x minus a from the Wikipedia example. So all this is right here, 231, is a matrix form of the expression above it. So what are we gonna? What are these going to end up being? This is going to end up being 0, 0, right? Because our goal is to get the constraint to reach 0. So we have 0, 0. What's this? This is going to be the value of the expression at our initial condition. We're still going to have an initial condition just like we did with the Gauss-Seidel. This right here is going to be a matrix with partial derivatives in them, okay? But they're going to be numbers. They're not going to be functions because we're going to plug in x1 and x2 of 0. We're going to plug in the numerical value. So we'll take the derivative and then plug in the value. So this will be 4 different numbers. And then this is going to be the desired value of x1, x2. This is your solution minus the initial condition, or the linearization point, the operating point, whatever. So 0, 2 numbers, 4 numbers, x minus a number. There's only 2 unknowns here, x1 and x2. And so what we can do is use a little bit of algebra, invert the matrix and all that type of stuff, and we will get a, thank you very much, a version of this equation where we can solve for x1 and x2. I want to know what she's doing over there that she's getting applause. I need to pick up some teaching tips. All right. So if we take 231 and we just use linear algebra to solve, we end up with 232. So x1, x2 is equal to minus times this same matrix. I used a little bit of a simpler notation. We know all of them are in terms of x1, x2, and u. So now I just started giving it the iteration number. Times the constraints with the initial condition plugged in, plus whatever the initial condition is. So this is a pretty self-evident iterative expression, right? Because what you do is you plug in your x zeros here, and it shoots out a new value of x, x1. Then you take these values, plug it back into the right-hand side, spits out new ones. Okay, and it's all based on this first order linearization. So it's not going to be perfect because it's the equivalent of trying to find the bottom. So this is a minimization problem, right? You're trying to find the bottom of a hill. The way that this works is it looks at the slope and it says, okay, well, the steepest slope downward is here. So I'll take one step in that direction, assuming that that's going to lead me to the bottom. Then I stop and I reassess and I say, okay, what's the steepest slope towards the bottom now? And then I take another step in that direction and just keep moving, moving, moving. So that's what this is doing. This is calculating what is the steepest slope towards our desired point. This right here is calculating how far away we are. Okay, so the further away we are, we may want to take a larger step in order to try to speed up the process. As we get closer, we may want to take smaller steps to slow down. And right, that's all going to be added. This is the length and the direction of the step that we're taking, and this is where we are right now. So this is x0, and I'm at x1, x2, etc. What you can do then is expand this expression for as many, or expand this formulation for as many expressions as you want. Okay? Let's say now it was a set of 10 nonlinear expressions with 10 variables. All you do is have x1, x2, x3, all the way down to x10. This becomes a 10 by 10 matrix. This becomes a 10 by 1. This becomes a 10 by 1. And it's all the same. The formulation doesn't change, right? You can just keep adding numbers to it. And so that's what I mean when I say that the Gauss-Seidel is different from the Newton-Raphson is different from the Gauss-Seidel, in that it's like this just stamp, right? You can just keep adding values to it and just make it bigger and bigger, and it doesn't change. Now, we haven't discussed how to find these values right here. Every time we end up having to take derivatives, everyone always cringes. And that part of it is not necessarily the easiest, but the good thing about it, again, is you won't have to take the derivative every time. The elements for the power flow problem, the elements of the Newton-Raphson matrix, there's only like 3 or 4 different kinds, right? So what we'll do is we'll take the derivatives at the beginning, and then you'll know sort of where to put things. If it's a derivative of P with respect to a voltage, we use this. If it's a derivative of Q with respect to an angle, we use this. And then just keep plugging it in. So we will have to do the derivatives, but we'll just do them once in the beginning, and then we'll use that as a model for expanding out. And so if we take 232 and represent it in an iterative form, you see your k plus 1s and your k's. Kth iteration of the values, output of the constraint functions, and this is called the Jacobian matrix. All right. So now what we're going to do, and I'm going to do this in the iPad, is we are going to apply the Newton-Raphson method to something that has nothing to do with power. Okay? Just to get an idea of how it works, and then what we'll do is branch out to the power stuff. If you look ahead in this set of notes, you're going to see like stuff gets really, really big really, really quickly. And some of the formulations for the Jacobian matrix, it just like, you know, you see, you're like, this looks ridiculous. We're going to go through it piece by piece. And like the way I think that the Gauss-Seidel looked initially, once you get through the nuts and bolts of it, there's a lot of patterns. And so you're reusing the same values over and over again, and you kind of, for lack of a better term, get the hang of it. Okay, so let's try this non-power flow Newton-Raphson example. All right, so what we want to do is we want to solve these two expressions right here. So we have G1 of x1, x2, and u, and that is equal to the only reason why we write it in this way is because we want to split up the constant component from the rest of the expression. And so that's going to be equal to 4u x2 sine x1 plus 0.6. So, sort of a randomish looking expression. So right off the bat, there is no good algebraic way we can see to solve something like this. Okay, you're not going to be able to isolate variables. You're not going to be able to use substitution to solve. You have x2 times sine of x1, and it's all mixed up together. So this is a pretty nonlinear. I mean, there's not that formally there's levels of nonlinearity, but from a qualitative or eyeballing it's very nonlinear, right? The expression doesn't provide any opportunity for solving using algebra. So how are we going to solve this? So So let's define the parts of the Newton-Raphson. We're going to calculate the Jacobian matrix. So the Jacobian matrix will be D, G1, for 0th iteration, D, X1, then D, G2, D, X2. D, G1, dx2, and dg2, dx2. I messed up one of the things here. Okay. So what are those values going to be? Let's do them one by one. So what's G1 derivative with respect to X1? When we're taking the derivative with respect to X1, X2 can be considered as a constant. So we're really looking at constant times sine of x1. So what is the sine of x, the derivative of sine? It's cosine. So you're going to end up with 4u x2 cosine of x1. And I'm just sticking in iteration numbers because we have them to the left. And the constant goes away. What's the derivative of the first one with respect to x2? Everything else will be treated as a constant, so we'll be left with 4u sine of x1 to the 0th iteration. Next, let's deal with g2 and do that and take the derivative with respect to x1. So the first term will go away. Second term will become a negative sign, so it'll be negative 4u x2 sine x1 0. Plus, minus, yeah. Okay, and then lastly, the x2, so it'll be 8x2 minus 4u cosine, can't forget my iteration, cosine x1 0, and that's it. Let's define our G matrices. Well, that's already done up here. So really, we have most everything. So define Jacobian matrix. All right, so let's set up our initial condition. I'm just comparing to see if everything right. 4u sine each x2 squared. So I'm going to follow the way that it's done in the notes. They don't plug in the numbers, they just have us get to the final update expression with the Jacobian matrix plugged in and it plugged in symbolically, and then we'll plug in the numbers using MATLAB. Okay, so what is our update going to look like? So we have x1, 1, x2, 1. First iteration, first update of our Newton-Raphson. So there's a -1 times our Jacobian matrix, which, frankly, there's no reason we have to write that again. So we'll just put here Jacobian matrix. Okay? We need to take the inverse of that. We need to multiply it by our g's. So our g's are 4u x2 sine x1, 4u x2 sine x1 plus 0.6, and then 4x squared plug in our initial condition and solve. So now you can see we have our expression in a form where the only thing we have to plug in are the x1, 0 and the x2, 0. There's lots of spots where they go. They go here, 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 here. So, I mean, you have to put them in a lot of places, but you plug those all in. And that's all you need. If you look at the MATLAB, again, you can see the steps in performing this analysis. And we run it, and we get a solution as shown. And if we take this solution and we plug it in to G, we should get values very close to 0, right? Because that was our goal in the first place. So it looks like we got -0.1669 and 0.9031. We plug those in, and the error is somewhere in 10 to the -4, 10 to the -5 area. So not too bad. Okay, now Newton-Raphson for power flow. We're not going to have a chance to get into this too much today, but